Hey, welcome back to your favorite calculus class. I'm going to take a look at version B on this PDF review here. Let's find the part A functional value f of -2, which is right there. It looks like it's defined to be 2. Then let's find f of 3. Notice that's a whole. The f of 3 is actually right down there. It's defined. F of 3 spits out an output of -1. Now let's go ahead and find our limit as x approaches 3 from the right-hand side. As we approach 3 from the right-hand side, notice it's approaching 0. We're getting iteratively closer to 0. I know it's not the functional value there, but that's the limit, right? We're approaching 0 if we approach 3 from the right. As we approach 3 from the left, it's also 0, and so the overall limit agrees. They both agree, even though there's a hole there, they both agree they get iteratively close to a y value of 0. Let's do it for x approaching -2 from the right, the next one, part F. As we approach -2 from the right, as we follow this function from the right, notice it is -1. I'm getting closer and closer and closer to -1. As I approach -2 from the left, and x value -2, I follow it from the left. I approach 2. When I approach -2 from the left, I approach a y value of 2. So the overall limit as x approaches -2, the overall limit, do they agree? No, they don't agree, right? We have a big gap right there. So this does not exist, the overall limit, because the left-hand and the right-hand limits do not agree. Now let's let's find the limit as x approaches -1. The overall limit as I approach -1 from the right and from the left. Do they agree? Yes, they do. That limit is 0. Now let's jump to part J on this. The limit as x approaches 3 exists. Yes, we did that. We determined that that was 0. So that is a true statement. Part B, f of x is differentiable at x equaling 3. At x equaling 3. Notice it's not defined there. Remember, to be differentiable, you have to be smooth and you have to be continuous to be differentiable at a point. You got to be smooth and continuous. This is not continuous. So this is actually false. And I apologize, my key is wrong on this. Let's answer the rest of these and we'll come back to that. Part C, limit as x approaches -2 does not exist. Notice we have that gap there, right? So the left hand and right hand limits do not agree. So that is a true statement. The limit does not exist as x approaches -2. F of x is continuous. F of x is continuous at x equaling 3. It's not continuous because I have a hole there. So that is false, right? Remember, to draw something that's continuous means you would draw it without lifting your pencil. Well, if I have a hole, I got to lift my pencil. So that is a false statement. This one's actually supposed to be the answer in your key. There's only supposed to be one statement that's false. Let's go on to E. The limit as x approaches 0 exists. It does exist as you approach 0 from the left and the right. It does agree. That is also a true statement. So I actually have two false statements on this one. So maybe I need to change this to like f of x is not differentiable at x equaling 3. If I made that statement, then that would become a true statement because it is not differentiable at x equals 3 because it's not continuous. If you notice on number 2b, if you plug 3 in, you're going to have 0 on the bottom. You plug 3 into the top, I got 9 minus 33 plus 24 is -24 plus 24. So I got 0 over 0 when I plug this in. So you can use indeterminate, you can use L'Hopital's formula. You've done that, or we're going to do this algebraically in this course. We'll practice our algebraic technique. So I'm going to go ahead and factor the top. So you notice this quadratic divided by a linear. If you remember from pre-calculus, if you have that canceling, that means you have a hole right there. you have a hole at x equaling 3. So this thing actually behaves like y equals x minus 8. It behaves like a linear. It just has a hole there at x equaling 3. Right? That's what this rational function is doing. And so that's why I want to simplify it by canceling that out, is because then I can rewrite it without the hole, and I could just plug it in. Okay, so your limit there just ends up being -5. All right, this next one, limit as x goes to infinity. Notice we have infinity over a negative infinity, so we're indeterminate. You could again use L'Hopital's. We could go ahead and practice our algebraic techniques. Limit as x goes to infinity, I've got square root of 4x squared plus 3x minus 5 over 7 minus 4x. So I go ahead and I take the largest denominator, power of my denominator, which is that x on the bottom, minus 4x there. Let me divide everybody by that x. Now, when I divide this by x, I want to get it inside the square root there. So square root of x squared is the same thing as x, right? If you want to be technical, that's the absolute value of x. But that's how I'm going to get it inside there, right? Square root of x squared over x. And let's keep going with this. So I've got limit x goes to infinity. I've got, so now all of this is under the radical, 4x squared. And I'm going to put each one of those because it's all divided by square root of x squared. And all under the radical. Over here I got 7 over x minus 4. And notice those x's cancel there. So we've got limit as x goes to infinity. I've got the square root of 4 plus 3 over x minus 5 over x squared. This is all over -4 plus 7 over x. Now let's go ahead and run this to infinity. 3 over a huge number, right, that goes to 0. Minus 5 over a huge number, that goes to 0. 7 over a huge number, remember x is going to infinity, that's 0. And so we end up with square root of 4 plus 0 minus 0 over -4 plus 0. So I got square root of 4, 2 over -4. So this just ends up getting a limit of -1/2. All right, notice on 3b here, we've got y equaling the cosine. Oh, so we've got quite the composite function here. So we say, well, all right, if I'm taking this derivative, dy dx or y prime, I say, what's the derivative of the cosine? Well, that's the negative sign of that stuff. And then I got to take the derivative of the inside there, right? I got to run my chain rule. So I take the derivative of the tangent, which is the secant squared, minus, and then I run the power rule on that, minus 2x to the 8th. So I got minus 2, and then I run power rule on that 8x to the 7th. And so dy dx just ends up being negative sine of the tangent of x minus 2x to the 8th times secant squared minus 16x to the 7th. All right, here we've got a function, and it's asking where is this function, and who knows what this looks like, but where does it have the tangent line 0, right? So we're going to say, okay, let's take the derivative and find where the derivative is equal to 0, has a slope of 0, right? Slope of the tangent line, that's our derivative. So we're going to go ahead and take this derivative using the quotient rule. So f prime of x equals derivative of the top times the bottom minus the top, derivative of the bottom, all over bottom squared. So f prime of x ends up being 2x squared plus 18 minus 4x squared over x squared plus 9 squared. So we're going to set that equals 0, our derivative. 2x squared minus 4x squared is a negative 2x squared plus 18 over x squared plus 9 squared. So where is this equal to 0? I'm just going to take my numerator, set equals 0. So 0 equals negative 2x squared plus 18. I'm going to add 2x squared to both sides. So 2x squared equals 18. So x squared equals 9. Square root, square root. So I got plus or minus 3 at an x value of 3 and an x value of negative 3. So that's step 1, is find that x value where that occurs. Step 2, if x is equal to 3, remember we want the point xy. If f of x, our original function, is 2x over x squared plus 9, f of 3 would be 2 times 3 over 3, squared plus 9. So f of 3 is 6 over 18, or 1/3. So we have one of the points is 3 comma a third. That's one of our xy values. And we also said it happens when x is negative 3. So f of negative 3 would be 2 times, again, I'm plugging it into the original function. And I get f of negative 3 equals negative 6 over 9 plus 9 is 18. So I get negative 1/3. So negative 3, negative 1/3. There's our 2 points. 3 1/3 and negative 3 negative a third. If I'm looking at number 5, I'm going to do both 5A and 5B just because they're a creative problem that's testing your understanding of the fundamental theorem of calculus. I really love this problem. If I look at this, the first thing I'm going to do is I'm going to be like, well, if g of x is the integral from negative 4 to x, then number 1, before I apply the fundamental theorem of calculus to take that derivative, notice these are all g of negative 1s over here, right? Or g primes and g double primes. And this is the function f over here. Okay, so what's the relationship? Well, if I plug in negative 1, then it'd be from negative 4 to negative 1, that's our x, of f of the function. So the integral from negative 4 to negative 1. Well, this integral is above the x-axis. So I know that integral will be a positive value. So I know g of negative 1 is positive. Okay. Now let's go ahead and let's find the derivative. So we have g of x is from negative 4 to x, f of t dt. So by the fundamental theorem of calculus, if I take this derivative, g prime, then it throws this in, it undoes the integral, f of x. Now, if this is something besides x, just make sure you take the derivative of that, chain rule. Like, for example, if it's not x, it's x squared, then I would say times 2x. Okay? But the derivative of x is just 1. So it just goes in. So g prime of x equals f of x. So g prime of negative 1 would be f of negative 1. Okay, let's find f of negative 1. F of negative 1 is right there. F of negative 1 is 0. Okay, so I know g of negative 1 is positive. I know g prime of negative 1 is 0 because it's the same as f of 1. And now number 3, if I take its derivative, so g double prime of negative 1 would be the first derivative at negative 1. Well, let's look at the graph. What's the first derivative at negative 1? Well, the first derivative of f is the slope of the tangent line. So let me go on there and let's draw the slope of the tangent line. I'm going to draw it in black. Slope of the tangent line right there. Well, that slope I didn't draw very good. But that slope, is it positive, negative, 0, or undefined? Well, that's going down and to the right. So that slope of that tangent line is negative. So now I can see which one it would be, A, B, C, D, or E. Well, g double prime of negative 1 is negative. So it's less than g prime of negative 1, which is 0. And that's less than the positive value g of negative 1. So it's got to be that one right there will be our solution. Let's take a look at this on 5 part B here. Let's do this similarly. Notice I have g of 2's over on the right as my options. So let's go ahead and use this first of all by just plugging 2 in. So 2 is my x. So I get negative 1 to 2 f of t dt. Notice this is the function f here, right? So from negative 1 to 2, the integral, now it's underneath the x-axis. So that's going to spit out a value less than 0, right? It's going to sum up all those rectangles and have a negative functional height, and it's going to be negative, right? Remember, if it's below the x-axis, we're finding the area, we'd have to take the absolute value of that, right? So we know that's negative. G of 2 is negative. That's number one. Number two, now let's apply the fundamental theorem of calculus and take the derivative. So G prime of x would be f of x. Again, that just goes in. Make sure you take the chain rule. Derivative of x is 1, so there's times a 1 on the end of that. So G prime of x equals f of x. So G prime at 2 would be the functional value at 2. Let's find the functional value at 2. There it is. It looks like it's 0. So G prime of 2 is 0. Number 3, G double prime at 2 would be the first derivative at 2. So the slope of the tangent line at 2. Let me go on here. Let's draw in black. Slope of the tangent. Notice that slope is positive, right? So this is positive. So let's write this in order. It looks like G of 2, that's negative. So that'd be less than G prime at 2, which is less than G double prime at 2. So it looks like that would be A right there. All right, given the derivative. Now, notice I'm not giving you the function. We're given the derivative. We already have the derivative, right? And so we're trying to find the critical number. So I'm like, oh, thank you for already finding the derivative for me. Let's find the critical numbers. So if f prime of x is 4x minus 2 over 3x to the 2/3, critical numbers would be, where is the derivative equal to 0? So I'm going to take my numerator there, set equals 0. So 4x minus 8, so, or I could just say x equals 2, right? 4x equals 8, x equals 2. All right, so that's where the derivative is 0. Where is f prime undefined? Well, when my denominator is equal to 0, so x equaling 0. And you could check that. Now, are they critical numbers? Well, as long as it's defined in the original function. So you could go to the effort of saying, yes, this is a critical number 0 by taking the integral of the original. We won't bother to do that, but it is defined in the original if you did take the antiderivative there. So both of those are going to be critical numbers, 0 and 2. So we want to go ahead and take f prime at -1. So let's go ahead and plug that in, f prime. So I got -1, if I got 4 times -1 minus 2, so I got a negative on the top, 3 times -1 to the 2/3. So I got 4 times -3, I got -12 on the top. Let me rewrite this as the third root, -1 to the 1/3. The third root of -1 is 1, but then I square it. So that's a positive value. I got 3 times 1, so I got -12 over 3. So that's negative. All I care about is negative. That means the function is decreasing. Let's go ahead and plug in like f prime at 1. That'll also be less than 0 if you plug that in. So we're going to be decreasing. Let's plug in f prime at 3. And you'll have a positive on the top. You'll have a positive on the bottom. So that'll be positive. The original function then must be increasing. So we are increasing from, let's go ahead and write this down, from 2 on, 2 to infinity. We are decreasing from -infinity up to 0, and then from 0 to 2. The relative max occurs. We have no relative max. We do have a min there at 2, right? It decreases, then increases. So we have a min at x equaling 2. All right, let's go ahead and do some integration with 7b here. If you see a radical, it's probably u sub with letting u be that radicand. So I'm going to go ahead and let u be 4 plus 3 sine theta. I'm going to try that first. So du d theta. Derivative 4 is 0. Derivative 3 sine theta. 3 stays there. Derivative sine is cosine d theta. Okay. So what I have here is I need 3 cosine theta. So I got to give this a 3 and offset it with a 1/3 out front. That's how I like to do mine. So this will become 1/3 integral from theta being 0 up to 2 pi of 3 cosine theta over the square root of u here. And again, notice that is our du. This is our u down there. So we've got 1/3 1 over the square root of u du. So we'll rewrite that as 1/3 u to the negative 1/2 du so that we can go ahead and run our power rule with that. So we've got 1/3 u to the negative 1/2 plus 1, so that'd be u to the positive 1/2 all over 1/2. Well, if it's all over 1/2, it's really multiplied by the reciprocal 2 over 1. Remember, this is from theta, being 0 to 2 pi. So let's go ahead and we have 2/3 u to the 1/2. U to the 1/2, our u here is, what is it, 4 plus, so 4 plus 3 sine theta, u to the 1/2 there, from theta being 0 to 2 pi. So I put it back into thetas so we could plug that in. So we got 2/3 square root of 4 plus 3 sine of 2 pi minus, now we plug in 4 plus 3 sine of 0. Well, we got 2/3 square root of 4 plus 3 sine of 2 pi is 0, minus 2/3 4 plus 3 sine of 0 is 0. So we have 2/3 times the square root of 4 minus 2/3 times the square root of 4. So 2/3 times 4/3 minus 4/3. So we just end up being 0 in this case. You guys have done initial value problems before. This is just kind of worded a little funny. It's got, find the solution to the differential equation. In other words, they're giving you the derivative, right? So you got the dy dt, and they want you to go back and find that initial function given this initial condition. So given y of pi 6 equals 6, if you have this derivative here, right? Number one, I have the derivative dy dt. Can I go back? Can I go back and find the original function? Well, sure. Let's take our dt over to the other side. Let's go ahead and run our integral here. And so the integral of 1 dy is 1y. Over here, I say, well, I got to let u be 3t, du is 3 dt. I need a 3 dt. Well, 6 is 2 times 3, so let me put a 2 out front and put the 3 right there. 2 times 3, of course, is still 6. And there's our 3 dt. There's our du part, and here's our u part. So we've got y equaling 2, integral the sine of u du. So now we can run the integral. The integral of the sine is negative cosine of u plus c. So y equals negative 2 cosine of u. Go ahead and put our u back in, 3t plus c. That's number one. So we have this in terms of c. So it could be a variety of functions because I don't know what my constant is right now. But I'm going to use the initial condition there. So number two, use this point that we're given, y of pi 6 equals 6. So I have y of t equals negative 2 cosine of 3t plus a constant. Plug in pi 6, negative 2 cosine of 3 times pi 6, and y of pi 6 is 6. So I got negative 2 cosine 3 pi 6, or pi halves, cosine of pi halves. We know the cosine of pi halves is 0. So I got negative 2 times 0 plus c. So I got 6 equals my constant. Now I have my constant, so I can go back and write the function. Y of t equals -2 cosine of 3t plus c. Well, our c here is 6. There is the solution to that differential equation. All right, number 9 is asking you, can you set up and then solve the integral, right, to find the area of the shaded region. So if you notice this area of the shaded region, we're going to set up a definite integral that goes from -7 to -5. This would be the area. It'll be above the x-axis, so I should get a positive value for this integral here, right? It'll be from -7 to -5 of the function. Well, the function is x squared minus 4 dx. So there's our setup on this. Let's go ahead and go down here and find this area. So you should get x to the third over 3 minus 4x from -7 to -5. So let's plug in -5 cubed over 3 minus 4 times -5 minus, now we're going to plug in the -7. There's 7 cubed over 3 minus 4 times -7. So -5, -5, -5, I got -125 thirds plus 20 minus -7, -7 is, let's see, that's -343 over 3 plus 28. Let me go ahead and distribute that negative there. So I'll have -125 thirds plus 20 plus 343 thirds minus 28. That'll give me 218 over 3. Let's see, 20 minus 28 is a -8. So I got 218 over 3 minus 24 over 3. So our area here is 194 over 3. You've got a particle here moving along the x-axis. Your velocity is given. So, maybe if I'm thinking about this visually, if my velocity is 8 root, you know what, that's supposed to be a t and a t. 8 root t minus t squared. Sorry about that typo there. Well, it's the distance traveled from 0 to 4. Let's say I graphed this and I found, I'm going to hit here at 0. I hit here again at 4 as well. So this is kind of what that would look like. So notice the velocity is all positive from 0 to 4. Right? The velocity is all positive. In other words, the particle is moving to the right. Right? And then it stops right here at t being 4. It stops at 4 seconds. And then the velocity after 4 goes negative. So then it goes back the other direction, right? But we just want total distance traveled from 0 up until 4, right? Total distance traveled. So I want to think I'm probably thinking to myself, remember we had position. Velocity is the derivative of position. So that's the one we're given as our velocity. And then S double prime or V prime is our acceleration. Now, we're not asked anything. Acceleration's not involved here, but I just want to remind you about those relationships, right? So if I go back, in order to find from 0 to 4 the distance traveled, right, the position at 0, the difference from there to the position of 4, I'm just going to integrate this. That'll tell me that whole integral of the velocity, right, would be the antiderivative of velocity at 4 minus the antiderivative at 0, right, the fundamental theorem of calculus. So that's what I want to do. I want to integrate the velocity from 0 to 4, and that'll give me the total distance traveled. Integrate velocity. All right, so we got 8 squared root of t, that's t to the 1/2. So 8t to the 1/2 plus 1 is up to the 3 halves, all over 3 halves, in other words, times 2/3. minus t cubed over 3. We're going from 0 to 4. And so we've got 16 thirds. I got 4 to the 3 halves minus 4 to the third over 3 minus 16 thirds, 0 to the 3 halves minus 0 to the third over 3. And so we got 4 to the 3 halves, so that'd be square root of 4, 2 to the third is 8. So I got 16 thirds times 8 minus 4 to the third is 64 over 3. And so we've got 128 over 3 minus 64 over 3. So the total distance traveled, since it all stayed above that x-axis there from 0 to 4, is just a straight up 64 thirds units, in whatever our units are, feet, meters, whatever, right? In terms of units, if let's say we are in feet, that'd be feet. Velocity would be like feet per second. That'd be feet per second squared. All right, on this one, as I take this derivative, I'm thinking about this in exponential notation instead of radical notation. So I'm going to write it as x to the negative 2/3 before I run this derivative. So y prime would be, or dy dx, so negative 2/3, x to the negative 2/3 minus 1, so negative 2/3 minus 3/3 is a negative 5/3, plus derivative of the cotangent is a negative cosecant squared x. If you want to look at your formula sheet, derivative of e to the 5x is ln of e, which is just 1, e to the 5x, chain rule on that derivative of 5x, which is just 5. So we got y prime equals negative 2 over 3x to the positive 5/3. I take that down, minus cosecant squared plus 5e to the 5x. 12b is asking us find the x-coordinate where there's a horizontal tangent. So again, I don't who knows what this thing looks like. Let's say it looks like this, right, or whatever. We're trying to find that x value where I have a perfect horizontal tangent. So we got to take the derivative, set it equals 0. So the slope of 0 would have that horizontal tangent. So let's go ahead and run the derivative f prime of x. So derivative, I have a product rule on this. Derivative of x plus 1 is just 1. Derivative of the first times the second plus the first. Derivative of 3 to the x. Derivative of the second. So ln of 3, 3 to the x, chain rule times 1, right? Let me go ahead and take out 3 to the x. So I'd have 1 plus x plus 1 times ln of 3. We distribute that ln of 3 here. So f prime of x, we want to know where this has a horizontal tangent, so I can set that equal to 0. 1 plus x ln of 3 plus 1 ln of 3, which is just ln of 3. 1 times the ln of 3. Now, where is this equal to 0? So I'm going to take each factor, set equal to 0. Where does 3 to the x equal 0? Where does 1 plus x ln of 3 plus ln of 3 equals 0? Let's go ahead and solve that one first. I'm going to take all my constants to the other side. Solving for x here. So I got negative 1 minus the ln of 3. Now I got to divide everything by ln of 3. This whole side by the ln of 3. So I have x equals negative 1 over ln of 3 minus ln of 3 over ln of 3. So x equals negative 1 over ln of 3 minus 1. So there's one x value where I have a horizontal tangent. Let's go ahead and look over here at 3 to the x. Where does 3 to the x equal 0? Well, if I'm doing this algebraically, I could either take the natural log of both sides, or I could just undo it with log base 3. Log base 3. So x equals log base 3 of 0. Well, that does not exist. The other way you can think about that, where does 3 to the x equal 0? Well, if you graph 3 to the x, it looks like this. It never does hit 0, right? There is no x value. It's always above the x-axis. It has a horizontal asymptote at y equals 0, so it'll never hit there, right? So nothing comes of that. You only have the horizontal tangent at that x value listed right there. 13b here, we're running implicit differentiation. So let's go ahead and take that through first before I run the derivative. Now I'm going to take this derivative with respect to x. So we got 4x to the third plus derivative of x squared, 2x, derivative of the first times the second, plus the first derivative of the second. So derivative of y squared, 2y dy dx. Right? Variables do not agree. I got to use chain rule because I don't know what y is. 2y derivative of y dy dx. Right? Equals derivative of y cubed, 3y squared dy dx. Chain rule. Again, I don't know what y is, so I have to say chain rule on that, dy dx. Now I got to get all my dy dx's on the same side there. So let's take this over. And so we have 4x cubed plus 2xy squared equals, and I'm going to take a dy dx out of both of these. Dy dx, 3y squared minus x squared to, oops, let me write that as 2x squared y. That'd be better. 2x squared y. Now, again, we're solving for dy dx. So let's go ahead and divide both sides by that. 3y squared minus 2x squared y. 3y squared minus 2x squared y. And so, if I take this up here, dy dx just ends up being 4x cubed plus 2xy squared over 3y squared minus 2x squared y. 14 is a question here, looks like on minimizing, maximum or minimum. So we're going to run that first derivative test. So let's take this derivative. Got to use the quotient rule. So derivative of the top times the bottom minus the top, derivative of the bottom, all over bottom squared. So it looks like we have, now what I want to find my critical point, so I'm going to set this equals 0. Let me distribute that. I got 10x squared minus 500x minus 5x squared over x minus 50 squared. So I got 10x squared minus 5x squared, 5x squared minus 500x over x minus 50 squared. And so where is this equal to 0? Take that 5x minus 100. So I got 5x equaling 0 and x minus 100 equal to 0. So x being 0. Now I want to actually produce something, so I'm going to throw that out, right? I'm going to reject that because we want to sell more than 0 units. So it looks like around 100 would be the test here. If I threw in, like, let's say c prime at 10, right? I plug it into the derivative here. Actually, let me put it in factored form. If I plug that, I'd have a, let's see, 5 times 10, that'd be a positive here. 10 minus 100, that'd be a negative right here. And the bottom is always squared, so it's always a positive on the bottom. So I get negative over a positive is a negative on this. So it's the original function is decreasing, right? And then I could plug in, I don't know, like maybe 110 here. Plug that into the derivative, you'll see that positive. So I just verified, oh, sure enough, there is a minimum there at x being 100. So x being 100 would minimize the cost. And that's kind of wraps it up. Hope that gives you a nice little overview of some of these problems for your department final, written by the department. Appreciate your efforts in the course. See you next time.